When we discussed the SN2 reaction, we talked about a few of the factors that affect the rate of those reactions. And we talked about the nucleophile, a lot of details about what makes better nucleophiles. We talked about electrophiles, what makes better electrophiles. And also we talked about the solvent for the SN2 reaction that was better for the rate and better solvent, therefore, for the reaction. In the SN1 reactions, the nucleophile doesn't actually matter very much because it doesn't affect the reaction rate. The reason is that it's not involved in that rate determining step because we have to wait for that leaving group to leave before that nucleophile can even attack. So it doesn't matter how good that nucleophile is, we won't be able to affect that rate because we do need to have that leaving group leave first. So that being said, the leaving group is very important for SN1 reactions because the rate is depending on how fast is that leaving group going to leave, and better leaving groups are going to be able to leave faster and make the reaction faster as a result. So, for example, if we have an iodine versus a chlorine, we would expect the reaction with the iodine to go faster because the iodine is a larger halogen. We kind of talked about those transition states as that iodine is starting to develop that negative charge in the transition state for that first step of the SN1. We're going to end up having it be more stable. That's going to be a lower energy transition state than the chlorine with that same developing delta minus. And so just like we saw with the SN2, because we were only focusing on that portion of the transition state we talked about SN2, we can actually directly relate that to SN1 because this is the only thing that's going on. That leaving group is leaving. So better leaving groups make the reaction faster. Also, if we have more stable carbocations, that's going to make the reaction faster. So in this case, they're both going to be tertiary carbocations. So we have three carbons attached to the alpha carbon in both cases. The difference is that in this one, we have a pi bond next to the alpha carbon. So once that leaving group leaves, we're going to be able to stabilize it. We're also going to have that partial stability of that partial delta plus, so that partial positive charge in the transition state as that leaving group's leaving because of this group here. And so we are going to see that lower energy of the transition state for more stable carbocations, and that's going to make that reaction faster because we're not going to be talking about full out positive charge in the transition state, but that developing partial charge, developing partial positive charge is going to be stabilized in the same way that the full positive charge would be. And so we could say that more stable carbocations will make the reaction faster as well, still thinking about that transition state. For the solvent, this one is actually a little bit opposite. So far for the electrophile, well, for SN2 reactions, we didn't really have to talk about carbocations because they didn't go through carbocations, but the leaving group was consistent. Better leaving groups make the reaction faster for both SN2 and SN1 reactions. For the solvent, this is going to be an opposite effect. So for SN2, we saw that polar aprotic solvents were going to make the reaction faster. And that was because the polar aprotic solvents, they weren't able to H bond, which was actually good because they wouldn't be getting in the way of that nucleophile getting to the electrophile. And that was really important for SN2 because that nucleophile was also involved in the rate determining step. When we take a look at polar protic solvents in our SN1 reactions, they do something different. So now we don't care if they're getting in the way in the nucleophile because the nucleophile is not involved in that rate determining step. It's not going to matter if they're H bonding with that nucleophile anymore. For SN1, it's all going to matter of how this solvent is going to help that first step of that SN1 reaction, that leaving group leaving. How much is this going to help it? And what the polar protic solvents can do, because they can H bond, we can start to have these H bonding interactions with the transition state for as the leaving group's leaving. And that's going to help stabilize that transition state. So these interactions are going to help stabilize that developing partial positive on the carbon, the developing partial negative on the iodine. So now we're taking a look at how solvent is actually going to help to stabilize the transition state as well, because we're going to be able to stabilize these developing charges. And so it's actually going to help the electrophile in this case to have a polar protic solvent. And because it's going to help stabilize those developing charges, were helping to stabilize that transition state, and that's going to make the SN1 reaction faster because this is to do with the electrophile. So if we have solvents like water, methanol, ethanol, these are going to be good solvents, good choices for SN1 reactions because they are going to be able to help stabilize that leaving group leaving, which is that rate determining step of the SN1 reaction. So a little bit different than our SN2 reactions. We don't have to worry about the nucleophile. We had a huge discussion on the nucleophile for the SN2, so that's all out the window right now because that's not involved in the rate determining step. Electrophile, same discussion about leaving group. For the carbocations, we're going to want to have more stable carbocations be possible because that's going to help stabilize the transition state. Not something we had to talk about for SN2 reactions because there weren't any carbocations. For solvent, though, we do see that the polar protic solvents are going to be better. So it's opposite than the SN2 where we wanted polar aprotic.